Section 13.3 is about trigonometric functions of general angles. We're going to look at angles of any size, and we're going to be able to find sine, cosine, and tangent by putting the angles in standard form. So here you see a picture of what we're talking about. If you take an initial side and you move it then to a terminal side, you create a triangle. That triangle has values x, y, and r for its three sides. I want to use this down here to show you that it can happen whether the terminal side is in any of the quadrants. So here, if I put a terminal side down in the third quadrant, you can see that it still creates a right triangle. The terminal side is r, the radius of the circle. If you imagine a unit circle around this, the x value is still here, the y value is still here. So we could talk about sine, cosine, and tangent of this angle, of angle theta, as being represented by those three values. And if you look up here into the key concept, you'll see what the sine, cosine, and tangent is. Sine y over r, cosine x over r, tangent y over x. And then the three inverse ratios are given just by flipping the sine, cosine, and the tangent. Here we're going to find the six trigonometric functions of an angle that has the terminal side at 0.5, negative 12. Well, we're talking about an xy coordinate plane here, so 5, negative 12 is somewhere down here in the fourth quadrant. I don't know exactly where it is, but I know it's something like this, and it would create this triangle. And so I'd have an x value here, I'd have a y value here, because it's positive 5, negative 12, and then I'd have a radius here. Well, I'm told that my x value is 5, and I know the y is negative 12, because I'm given the point there. So all I have to do now is find the third side of the triangle. The way we do that is use the Pythagorean theorem. So I can use c squared equals a squared plus b squared to find my radius. Now, I'm using a, b, and c rather than x, y, and r. I hope that's okay. C is the hypotenuse, so that's the one that we don't know. We'll say a is the 5 and b is the negative 12. So c squared is 169. Take the square root of both sides, and we find out that c is 13. Now, that's using the Pythagorean theorem. If we're going to call our three values something over here, we're going to say that x is 5, y is negative 12, and then r, which is our c, or the hypotenuse, is 13. These three values are crucial for us finding the six trigonometric functions. So if we go back to the key concept, we'll see that this is how we find sine, this is how we find cosine, and this is how we find tangent. And we can just plug our values for x, y, and r in. And so here you see sine, cosine, and tangent. And then by taking each one of them and providing their inverse or flipping the fraction, you can see cosecant, secant, and cotangent. So we have all six trig functions from an angle where its terminal side is along 0.5, negative 12. Here we'll take a look at what happens when the terminal side of the angle lies on one of the axes. So if I have the initial side here on the x-axis and I have a terminal side that lies on one of these, in our example it says the terminal side is going to be on 270. That's going to be this case right here. We're talking about an angle theta that looks like that. And furthermore, if we put this as a point down here, a point that we don't know, we know that that point is 0, negative r. By r we mean the radius of a circle that we could draw around this. So this point is 0, negative r. And you see that example right here along with some of the other examples for quadrantal angles. These are angles that actually lie on the x or the y axis. So we're going to find the six trig functions of this angle here. But I want to point something out to you. This 0 is your x. This negative r is your y. And for the radius of the circle, we don't know, so we're just going to call it r. So our x, our y, and our r are given to us right there. And I want you to see a couple of the interesting things that happen with the six trigonometric functions. So here we see the six trig functions. Let's look at sine first. Sine is y over r. Well, we said that y is negative r over r. Well, anything over itself is 1, and this becomes a negative 1. So the sine of this 270 degree angle is negative 1. Cosine is x, and we said x was 0 over r. Here's where we don't even need to know what the radius is because 0 over anything is just 0. So the cosine of theta is 0. And then y over x, y is negative r, and x is 0. When you divide by a negative, you get something that's undefined. So it turns out that the tangent of a 270-degree angle is undefined. The other three, you're just going to take those two fractions and flip them. So r over negative r. Cosecant then is also negative 1. Secant's going to be r over 0. So the secant is undefined. Cotangent is 0 over negative r. So the cotangent of a 270-degree angle is 0. Here we will introduce something called a reference angle. That's the acute angle, an angle less than 90 degrees, that's formed by the terminal side of theta and the x-axis. So I want to draw your attention over here to the first quadrant, because that's what this is. This is an angle drawn in the first quadrant. The terminal side is in the first quadrant, and so therefore the reference angle is the same angle. It's from that terminal side to the x-axis. Now if you look over here in the second quadrant, you see that the terminal side stops, so this is an angle that's bigger than the 90 degrees, so we call this small angle between the terminal side and the x-axis, that's called the reference angle. So if this big one were 150, let's say, it's a 150-degree angle, then we would say that the reference angle to that would be 30, because that's the distance to get down to a 180-degree angle, and that's the reference angle. Here in the third quadrant, you see an angle that wraps all the way around, has a reference angle that goes from here up to the x-axis, and then finally in the fourth quadrant, you wrap all the way around, but your reference angle is this small angle between the terminal side and the x-axis. So here we're going to sketch the angles and then find the reference angles. Here this is a 360-degree angle, so that's going to get us somewhere over to here for our terminal side. And that loops around this far. And so that's 300. I know the whole way up, the whole way around one time is 360. So I could do 360 minus 300. I know you can tell that that's a 60 degree. So that means that this reference angle here is 60 degrees. That's the small angle between the terminal side and the x-axis. Over this side, negative 2 pi over 3. I don't know about you, but it's harder for me to draw these angles when they're in radian form. So I like to take them and convert them into degrees by multiplying by 180 over pi. So this ends up being a negative 120-degree angle. So I know I'm going to go down into this third quadrant, have a terminal side that's here. And I know that this is negative 120, which means to get up to 180, there's got to be 60 more degrees that I'm looking to get. So then this little reference angle here could be a 60-degree angle. But if it starts in radians, I'm going to want to make sure that my answer is in radians. So I'm going to take 60 degrees, and I'm going to convert that into radians by doing pi over 180. So 60 and 180 is 3. So this reference angle is going to be pi over 3. Okay, so here we want to find the sine of 120 degrees. But the difference is it says we want the exact value. So we cannot just put this into our calculator because our calculator gives us a decimal approximation. So we're going to use what we've learned today to find this. We know that 120 degrees brings us into the second quadrant, somewhere like that. So this here would be 120. And then that gives us what kind of a reference angle? That's going to give us a reference angle of 60 degrees. That's important because if we're going to use sine of 120, then really we can find the sine of 60 degrees. That's what the reference angle's for. They're the same values. Well, what's the sine of 60? You got to go back to what we did in section 1. You'll find this on page 703. This is a table that you had if you printed out the notes. But you see on the table here that if you have a 60-degree angle, the sine of that is square root of 3 over 2. That's the sine of a 60-degree angle. So we can just say that this is a square root of 3 over 2. Which means also that the sine of 120 is also the square root of 3 over 2, but one thing we have to check for is make sure that the sign is okay. The way you check the sign is by thinking about the four quadrants. In the first quadrant you have positive ordered pairs. In the second quadrant you have negative positive ordered pairs. In the third quadrant negative negative, and in the fourth quadrant positive negative. Now for sine, cosine, and tangent, if you have an ordered pair up here, you're going to do, remember, the x value goes to the right and the y value goes up, and you make those imaginary triangles that I talked about at the beginning. And you can do that in all four quadrants. Without taking up the time to show you every example, what happens is that all these quadrants are made up of ordered pairs that give us cosine, comma, sine. So in all of these quadrants, it's cosine, sine. So when you find the sine or the cosine in any of these quadrants, these signs match up with them. So if we say a sine of 120, that's in the second quadrant over here, is sine positive in the second quadrant? And we see yes, it is. So we can say the sine of 120 degrees is positive square root of 3 over 2. Here's another example. We have to find the exact trigonometric function, but this time it's in radians. I'm going to take those radians and convert it to degrees by doing 180 over pi. So 4 goes into 180 45 times, and the pi's will cancel. So this is really a 315 degree angle, which brings us around to about here. That means our reference angle is going to be a 45 degree. So we are actually going to look for the cotangent of 45 degrees. That's a lot easier to find. Now, cotangent is the opposite of tangent, the inverse of tangent, I should say. And I want to show you something about tangent. That's kind of cool. Since sine is y over r and cosine is x over r and tangent is y over x, take a look at this. If I take sine, which is y over r, and divide it by cosine, which is x over r, now y over r divided by x over r, that's really y over r times r over x. The r's will cancel. So if I take sine and divide it by cosine, I really get y over x, which is what tangent is. So that leads me to this. I can take sine, divide it by cosine, and that equals tangent. And this is something that you definitely need to write down, because this idea that sine divided by cosine equals tangent is going to be very important to us as we continue to go on. But that also means that cosine over sine equals cotangent. So if I'm looking for the cotangent of 45, what I'm really looking for is the cosine of 45 over the sine of 45. And I like 45s because I can go back to this table again and say cosine is root 2 over 2, sine is root 2 over 2. Oops. So this is root 2 over 2 divided by root 2 over 2. Well, guess what? Anything over itself is 1. So the cotangent of 45 is 1, which means the cotangent of 315 is 1, and also the cotangent of 7 pi over 4 is 1. Now the last thing we have to do is check the sign. Remember, because we're in the fourth quadrant, we have positive negatives, and we said that all those points are cosine first and then sine. Well, since cotangent is cosine over sine, I'm going to get a positive divided by a negative, which equals a negative 1. So finally we get the cotangent of 7 pi over 4 equals negative 1. Here we see that an angle in standard position has the terminal side in quadrant 3, which means it's going to be here in quadrant 3, and it's going to make a triangle. We've discussed this in the past. The secant of theta is negative 4 over 3. Now secant is the inverse of cosine, and secant is found by doing r over x. So we know now that the radius We know now that the radius is 4 and the x value is 3. Since 4/3 is negative, we're going to put the negative with the 3 because it makes sense to go to the left and make it a -3, and then our hypotenuse is going to be a positive number. So what we don't know is we don't know the y. Well, we've done this in the past. We can use Pythagorean theorem. C squared equals a squared plus b squared. So my hypotenuse is 4. My a value is -3, and my b value, which is my y value, I don't know. So subtract 9 from 16. I get 7 equals b squared. So b is the square root of 7. So my y value here then is the square root of 7. Now this is a plus or minus, and because we're in quadrant 3 and we're going down, then we're going to say that our b is actually negative square root of 7. So that's also our y value, negative square root of 7. So x then is -3, y then is negative square root of 7, and the r is 4. We'll use those three values to find the 6 trigonometric functions. So here we have all 6 functions. We were given secant. We could find sine, cosine, tangent, cosecant, and cotangent. One thing about the last two is they have square roots in the bottom, so they need to be rationalized, those denominators, and so that's where we get the square root of 7 times square root of 7. Here you have a unit circle that has a ton of information on it. You're going to get one of these in class, and if I don't remember to do it, remind me, because this unit circle really is going to go a long way to helping you understand and solve problems as we go forward.